Hello guys, welcome back to my channel Gamma Di Gamma. In the last video we developed the idea of a Fourier transform. I give examples and generalized it to higher dimensional spaces. In this video I would like to give some useful properties of the Fourier transform, and maybe if there's space in this video talk about some convolution ideas. But I might just make another video for convolution. I'm trying to keep my videos short according to some recent feedback from my channel. So let's get started. So the last bunch of videos we developed this idea that Fourier transform of a function f of t, which we denote as capital F of omega, is 1 over square root of 2 pi integral over the whole space, which is from minus infinity to infinity, dt e to the negative I omega t f of t. This is a time Fourier transform. Okay, and then the inverse of this. So how do we obtain f of t back again? But it's by plugging in the capital F of omega in this inverse Fourier transform integral over omega with e to the I omega t f of omega. Fair enough. But the better idea, if you're in a applied versions of math or physics or whatever, is to think of these things as an operator, an integral operator, if you will. So instead of just plugging in the input, which is f of t for the transform case, the operator is just everything without the f of t. This is your Fourier transform operator. And equivalently, inverse transform operator is 1 over square root of 2 pi integral from minus infinity to infinity d omega e to the I omega t, which accepts functions of omega. And one thing to kind of notice here is if I consider f of t to be an eigenfunction, or sort of like the generalization of a vector, if you have an infinite dimensional vector space, then eigenfunctions make sense. Then what these operators do is they take in the vector as an input and they spit out another vector. So they're sort of linear functionals, but linear functionals output a real number. So they're sort of the generalizations of tensors. It's like they're like a matrix. Multiply a matrix with a number or a vector, you get another vector. So linear function is not probably the right term. It's tensors. It's a mixed order. It's something between a vector and a linear functional. It has rank 2, but these are more broad ideas, and I won't really talk much more about them. I'll talk more about them in the tensors video. Hopefully we get there soon. So one thing we can do with this idea is, you see this formula for the inverse, and you see there's an f of capital F of omega here. Why don't we plug this guy in over there? But one thing to note, that the t here is not the same as the t there, because these integrals are independent of each other. The only thing that's the same is this omega, because this omega here was involved in this integral as well. So with that in mind, I have 1 over square root of 2 pi integral from minus infinity to infinity d omega e to the I omega t. In place of this, just take this integral in. So 1 over square root of 2 pi integral from minus infinity to infinity. Well, now let's just change the variable name as discussed before. Call it t prime e to the I, same omega but different t prime. And we have an f of t prime. Yep, that's it. And now I would like to club these square root factors to 1 over 2 omega, 1 over 2 pi, sorry. Integral from minus infinity to infinity. Let's see. D omega. We can club some terms. Oh, dt prime e to the I omega exponent property t minus t prime f of t prime. Fair enough. Now, assuming conversions, uniform, whatever, all that stuff, I can interchange these integrals, and this will be the case because these functions will be convergent. They will be nicely behaved. Otherwise, Fourier transform will not exist if the integrals diverge themselves. And we have integral over d omega, this crazy thing, f of t prime. Now I would just like to do one step. I would like to take the 1 over 2 pi inside because I want to prove a point. So I take the 1 over 2 pi, everything else is the same. D omega e to the I omega t minus t prime f of t prime. So notice the integral inside, we're integrating over omega. So the resultant function will be a function of t minus t prime. So let's just call that g, this entire thing in the bracket. So it's a function of t minus t prime, let's call it g of t minus t prime, times f of t prime, integrate over t prime, gives you f of t, because that we picked this up from this definition here, the inverse Fourier transform definition. So what function, this is the question you need to ask yourself, what function sort of multiplied with this t minus t prime and then integrated with itself over this entire interval gives it, it itself evaluated at t. The idea is, if you remember a special function called the Dirac delta function, this is the only function which will help us in this case, at least as long as we have an integral inside, because notice you integrate over dt prime of Dirac delta and f of t prime, you'll simply get an f of t. Just watch that video if you sort of forgotten it or don't know what this is. This is a really useful idea, and I'm glad this came before Fourier transforms and Fourier series. So what does this mean? G of t minus t prime was just this integral inside the brackets. And we know that to be the delta function, because that's the only function that will satisfy this property of this integral. So which means the delta is 1 over 2 pi, integral from minus infinity to infinity, d of omega e to the I omega t minus t prime. And there we go, that's the definition. So you integrate over something, you take that outside, e to the I omega, and then t minus t prime, that's just the argument of the delta. You have a 1 over 2 pi normalization and integrate over an entire space. That's your formula. Extremely important. I can't stress how important this is for quantum mechanics, and not just quantum mechanics, just for everything that's going to follow just in this video series. So I hope you remember this. Really useful. Okay, so let me just write the operator form of this. We know this is Fourier transform. Say this is one function. So you have another function, g of t. The fact is, just by the way the integral is defined for the Fourier transform, these final transforms can be complex numbers. The only one thing that we know is real is this omega, because that's how we defined it from the start. So this omega is real, this frequency is real. But you'll see in the case of Laplace transforms that may not be the case. And that's why Laplace transforms are way more general. So the first property is called a time delay. Why is there time delay? Because if you have a function that's sort of shifted up, the t minus t naught inside, let's see what this evaluates to. Let's just plug it into the definition. If f of t minus t naught. Let me use a substitution. That's the classical way of doing these things. So d alpha is dt, so no problem there. Again, doesn't affect the infinities. So d alpha negative I omega t is alpha plus t naught f of alpha. So we can pull the t naught outside. E to the negative I omega t naught. Everything else, just write it as it is. And just notice now that this, apart from the first exponential prefactor, is just the Fourier transform of f. We're just integrating with variable alpha, but that doesn't change because it's a definite integral. That doesn't change what this expression means. Or more precisely, e to the negative I omega t naught f of omega. There we go. That's the formula for a time delay. Fourier transform of f of t minus t naught. So this kind of makes sense because this term is sort of the phase difference in the complex plane. So a time delay here on the real plane is like a phase difference in the phasor in the complex plane. So if f of omega can be represented as a phasor like this, with some angle. So if this is the magnitude of the phasor is the real part of this, and then you can define a phase by writing this complex number f of omega as in terms of its polar decomposition. Then having a time delay just means that it's now going to have sort of different phase. So you're going to have a phase difference here while you have the same magnitude. Because you can take the magnitude of this and you get the same magnitude as before. Just the phase difference is different now. So in some intuitive level, this also makes sense. Let's see what's new. So there's a time inversion property. Of real functions. And by real functions, I mean these input functions. Precisely, f of t is real, so by time inversion, I mean if I have a negative argument here. Let's see what that does. Again, we can do a nice substitution there. D alpha is negative dt. So this just flips the integral around, plus infinity and then minus infinity. D alpha f of alpha so if 1 over square root of 2 pi, use the negative to flip this in the right way. Now notice what this is. We know f of alpha is real, but if you just consider the operator itself, if you just consider this operator, this was the Fourier transform operator, and you take a complex conjugate of this, it's gonna change. It's gonna also take the complex conjugate of the things inside, because nothing on the outside is affected by this complex conjugate. So it's gonna make this minus to a plus. That's how the complex conjugate works. And since f of alpha is real, if you take conjugate on say something like this, then it's gonna keep f of alpha unchanged, just complex conjugate as before on the exponential factor. So that's what this thing is precisely. And of course, we have the 1 over square root normalization factor that I keep forgetting here. This is precisely the complex conjugate of the Fourier transform of f. I hope this argument convinces you. You can always check it out on your own. Now, this is useful because if we have even and odd functions, what I mean by that is a function is even if f of negative t is f of t. Something like cosine, for example. Except you'll have to sort of normalize the cosine or have a different function because a cosine will diverge at infinity and negative infinity if you take a Fourier transform. By time inversion property, this will become the complex conjugate of the Fourier transform. This is just the Fourier transform. This means that Fourier transform is purely real, because that's when a complex number is equal to a conjugate of itself, when it's purely real. Similarly, if you have an odd function, something like a sine or like a sine wave function, then you use your similar property. This time you have negative f of omega. Any complex number that's negative of its complex conjugate is purely imaginary. So these arguments are really helpful in quantum mechanics. We're talking of wave packets or wave functions. And mind you, all these properties in green, from time inversion to purely imaginary, are only applicable for f of t being a real function, because that's when the time inversion property applies. You can only take a complex conjugate like this or conclude that this is the complex conjugate of the Fourier transform as long as f of t is real, because if it weren't, you'd have to also take the complex conjugate of f, which may not be the same as what it was before. Now, a very important property is about derivatives. Again, this is really important when we're going to apply Fourier transform to a set of differential equations. So assume you have a derivative now as an input. Instead of f of t, of df of t of dt. So 1 over square root of 2 pi. I'm just writing the definition and let's see what we can do from there. Your natural instinct at this point should be look at this derivative and look at everything else to use integration by parts, because we know the integral of this by the fundamental theorem of calculus. That's just f of t, while we differentiate everything else. So first just take the integral bit, that's f of t, negative infinity infinity, minus, and you differentiate this, so you get a factor like this. Don't forget the dt, and integrate, so f of t. This is just integration by parts. Now, since f of t is a function that is well defined or has a well defined Fourier transform, it must go to 0 at those endpoints when t goes to plus and minus infinity. Otherwise, the integral of the Fourier transform will never converge. So this should be the case for Fourier transform integral convergence. Because that's the case, this term entirely goes to 0. Because all this complex exponential does is just changes the phase in the complex plane, just keeps rotating in the complex plane. The magnitude is determined by f of t. Now, anyways, we have negative and negative I omega dt e to the negative I omega t f of t. This is just I omega times the Fourier transform of f. So that's f of omega. Really useful property. You can see if we keep taking the derivative this way, we keep increasing the power of I omega. So the nth derivative, for example, just keep increasing power, this power. That's how powerful this is, because if you apply this to a differential equation, it reduces down to a linear equation in I omega, of which I can be sort of cancelled out. It's just a constant. You solve for omega, and that is sort of the frequency you were considering, and then you invert the Fourier transform. So it's a really powerful method. This video has already become extremely long, so there's no point in talking of convolution in this video. See you in the next one. Peace out. Stay safe.